Okay, so we just gotten the acceleration for the second part, and it's a negative because the parachute is slowing the buddy down. The negative means up, or that they're slowing down, going down. And we were calling down positive. Okay, and so with that then we can find how far did it travel in the second part. VI delta t, 1/2 a delta t squared. The VI was 48 meters per second down, times 10 seconds, plus 1/2 negative 4.3 meters per second squared, times 10 seconds squared. So the first term will be 480 meters, and the second term will be 2.1, or no, not point, because I forgot to multiply by 100, 215. So delta D will be equal to 265 meters for delta D2. Okay, that becomes important so we can get the delta D3, because delta D3 is going to be equal to the total 3,000 meters minus the delta D1 and the delta D2. So 3,000 meters minus the 144 and the 265. And so that should give us a delta D3 of 2,591, I think, meters. If I did that right in my head. 3,409. Yeah. Okay, and so now that we have that, we can find our delta T3. Because VAV is equal to delta D over delta T. So delta T3 is equal to delta D3 over VAV. So 2,591 meters divided by 5 meters per second. Delta T3 should be equal to 518.2 seconds. Okay? Once we have that, we look at the question, and it says, how long will it take? So you add 6 seconds, 10 seconds, and 518 to get a delta T total of 534, I believe, 0.2, assuming that I did that correct in my head as well. Okay? And that's it. That's all it asked. All right. On the back side of the sheet, we had numbers 4 and 5 to do. Okay, so a student in a window on the second floor of his school sees his physics teacher, I'm just going to move it out so I can actually see it, sees his physics teacher coming along the sidewalk beside the building. He drops a water balloon from 18 meters above the ground. All right, so a water balloon is up here, okay, and it's 18 meters above the ground. The teacher is over here walking this way. So the two sections are going to be the balloon and the teacher. So he drops the balloon. VI will be 0. It falls, so its A is going to be 9.81 meters per second squared down. Okay, he drops a water balloon 18 meters. The teacher is 1 meter away from directly being below it. The teacher is 170 centimeters tall, or 1.7 meters. So if he wants to hit the teacher on the head, the delta D for the balloon will be 18 meters minus the 1.7 meters. So the delta D will be 16.3 meters down. The teacher's walking, and her delta D is 1 meter. And they're walking at a speed of VAV, because they don't know they're about to walk into a water balloon, of 0.5 meters per second. Clearly the bell hasn't rung. They're not going fast. So you want to know, will the balloon hit the teacher? It'll hit the teacher if, by the time the teacher gets here, if the water balloon is right at the teacher's head. So first step would be find the time for the water balloon to reach where the teacher's head would be, and then I'd probably check and see with that time, where is the teacher? So first step, let's find the water balloon's time. So delta D equals VI delta T, 1/2 A delta T squared. VI is 0, so t squared is equal to 2 delta t over A. So 2 times that's 16.3 meters divided by 9.81 meters per second squared. Remember, that's t squared, so when you punch this in, don't forget to take the square root. So 32.6 to divide it by 9.81 and take the square root. 1.8229. 1.8229 seconds. Okay, so I would use this, and I would go over here and use VAV is equal to delta D over delta T, and I would find the delta D of the teacher. VAV times the time of the water balloon, just to see where the teacher is. So 0.45 meters per second times that 1.8229, and there are other decimals there, so keep it all in your calculator, multiplied by 0.45, and you get that the teacher is 0.8203 meters away. 0.8203. So they're not quite there. They're about 18 centimeters from the balloon falling in front of them, which to me would say they're not going to get hit. So no, not on the head. But then the second part of the question says, will they get hit at all? So will they walk into it maybe? Like, will it fall in front of them? So to find that, do exactly the same thing, but this time use your delta D as 18. Oops, put a 2 in here. 2 delta D over A. Use your delta D as 18 meters over 9.81 meters per second squared, and find the time it takes it to go all the way to the ground. So 36 divided by 9.81, and take the square root. 1.91565 seconds, and then take this and do the same thing. Find where will the teacher be then. So delta D of the teacher will still be VAV delta T. The VAV is still 0.45 meters per second, but this time the delta D is 1.91565, etc. So the time you have on your calculator by 0.5, it's just 0.862. So it's going to hit the ground in front of her. It will probably break and splash, and she'll get wet, but it won't hit her on the head. And maybe you won't totally lose all of your points for your class mark. All right, number 5 says a dropped object passes a window. And we're probably going to run out of time before we get this one done. A dropped object passes a window that's 1.3 meters tall. What height above the window? So the two sections, above window and window. Above window, it's dropped. Its VI is 0. A will be 9.81 meters per second squared down. A dropped object passes a window that's 1.35 meters tall. That's the delta D of the window. A for the window is also 9.81 meters per second squared. And it says it passes the window in 0.21 of a second. From what height above the window was it released? You're looking for the delta D up here. And what you know is the VF of this section will be the VI of this section. If you can find one, you will get the other. Where do you start? You should start with the window because you only have one unknown. Once you find that, then you can find the delta D. So with the window, I would use delta D is equal to VI delta T. 1/2 A delta T squared, because you have the delta D, the A, and the delta T. Rearrange for this for the VI, so take this term over. So delta D minus 1/2 A delta T squared. You want the VI, so divide by delta T. So VI is equal to, and everything's going down here, so you don't really have to worry about negatives. You can call them all positive. So 1.35 meters minus 1/2, 9.81 meters per second squared, 0.21 of a second.